Thank you very much for that kind introduction. And also, as I get started here on my talk this afternoon, I would certainly like to thank our hosts here at the Catholic University of Temuco for the opportunity to participate in this discussion, listen to all of the very interesting presentations, and also to contribute to the dialogue yesterday and today. As noted, my name is James Groves, and I'm a faculty member in the engineering school at the University of Virginia. And in our discussions yesterday and today, we've heard a lot about mathematics and science education. And this afternoon, I'd like to turn our attention to engineering education. And most specifically, I'd like to focus in on education in the area of engineering design. And I want to give you a little bit of a flavor for how we teach students engineering design at the University of Virginia, and I'll talk a little bit about how we combine the technical understanding and design work with thoughts about society and also thoughts about globalization. So as I get started this afternoon, what I'd like to do is just first of all give you a quick orientation. Where is the University of Virginia? Certainly up there in North America. But here we have Washington, D.C., the nation's capital in the United States. And the University of Virginia is about a 2-hour drive by car to the southwest. We have mountains, not nearly as tall as the Andes, but we have the Appalachian Mountains that are some of the oldest mountains in the world. And of course the Andes are some of the newest mountains in the world. Actually, our university is a United Nations National World Heritage Site, and this is one of our very pretty historical buildings, the Rotunda at the University of Virginia. Overall, as a university, we have over 2,000 faculty members, 15,600 undergraduate students, and 6,300 graduate students across the many schools of the university. Now, as mentioned, I'm a faculty member in our School of Engineering, and our engineering school was founded in 1836. And what you see here are the different departments of engineering that we have, both education as well as research active. So we have biomedical engineering, chemical, civil and environmental. The computer science programs are included within our School of Engineering. We have electrical and computer engineering. We have a department that we'll talk more about as we go through the next half an hour, called the Department of Engineering and Society, and it is one of my home departments. My other department is actually the Department of Material Science and Engineering, Mechanical and Aerospace, and then Systems and Information Engineering. And across these many departments, we offer 11 different degree programs, bachelor's degree programs. In the engineering school itself, we have 175 faculty members across these departments, 2,700 undergraduates, and 600 graduate students working with our faculty on cutting-edge engineering research. Now, there are many engineering programs in the United States. In fact, there are over 400 different colleges and schools of engineering in the United States of America. And so one of the things I like to do when discussing and describing the programs of the University of Virginia is to try to describe to you what is it that we believe is distinct, perhaps special, about the way that we teach our students about engineering. So we certainly are working to develop leaders. And we talk about working to develop leaders of innovation. And so within our undergraduate program, as a student works towards their bachelor's degree in engineering, our bachelor's degree programs typically take 4 years for students to complete. And we work on a credit hour basis. And so students working to complete the undergraduate degree in engineering will complete 128 credit hours for their bachelor's degree over a 4-year period. Now, like the many other engineering programs in the United States and certainly around the world, we're interested in making sure that our students have technical competence, that they understand the math, the science, the engineering concepts that come together to allow them to design solutions to challenges. And so we certainly want to make sure that our students have technical competence. Today we're going to talk a bit about design engineering and design. And so within our coursework that provides technical competence, we require our students to take at least 9 credit hours of engineering design studies. And some of that begins actually in their first year of undergraduate studies, even right in the first semester. Something that we do in our engineering program that I think is a little bit different than what you'll find in many of the engineering programs in the United States around the world is we also work to make sure that our students appreciate what we call engineering in context. And we'll talk a good bit about this as I go through my comments in the next few minutes. But the idea of engineering in context is that we want our students to appreciate, to really understand that to be successful as an engineer, you need to understand more than just the technical know-how. How do we make this device function? But you need to understand as a student, ultimately as a practicing engineer, that there are ethical considerations, that there are cultural and societal considerations, there are government rules and regulations, and there are business dimensions. And all of these factor together that the students not only have to create a functional engineering solution, but they need to appreciate perhaps the culture, the government that they're seeking to introduce their solution into. They need to understand the government rules and regulations. They need to understand certainly how to finance their solution. And so in addition to working with our students on their technical understanding, we really work to make sure that they also understand engineering in context. And so we require of our students 12 credit hours of this engineering in context studies. As noted, before I go to that next comment, when I teach students in the engineering school and I teach them about engineering design and also try to help them understand engineering in context, as an instructor, I'm certainly also working to build their critical thinking skills. We've seen this sort of diagram earlier in the presentation. There are certainly critical bits of information, facts and figures that students need to remember and understand. But in the education programs, we also certainly want to drive them to the higher order thinking skills, all the way up to where they are creative and innovative engineers coming up with new solutions. And as we teach them, our overall goal is to prepare those students to contribute to a better world for all of us. So, engineering design, and this is what I want to focus on for the next few minutes, is a course that we begin to teach, an area of study in our engineering school that begins right when our students arrive at the University of Virginia, and they join the engineering school for the first of their 4 years of study. And I teach students at this level about the design process. And so I'll talk about design today, and I'm going to organize the talk around the steps of the process as I lay them out for the students in the classroom. We begin in our studies of engineering design by defining a challenge space. And when I think about a challenge space, I use in English the word challenge as opposed to problem. Often we talk about engineers as being problem solvers, but in English, problem has a bit of a negative connotation, a negative meaning. And so challenge can mean engineers addressing a problem or engineers recognizing an opportunity, something positive, something new that they contribute to developing. And so initially, the students in the class need to be able to define, to identify a challenge, a problem, or an opportunity. They then need to be able to generate different ideas, to be innovative, creative in their thinking. How are we going to address this problem or this opportunity? So they generate and select a set of solution concepts. And then once they select what they believe is the best, most promising solution concept, they have to go through and they have to explore, and they have to study, almost in a scientific method, run experiments to see, is their solution concept really a good, viable solution? Is it capable of addressing the challenge that they've identified? And then at the end, similar to what Charles Grisham talked about earlier today in his discussion of chemistry education, our students have to be able to communicate and report their findings and make recommendations about their design solution. Now, as they do this, the students are going to be, in our engineering school, focused not only upon the technical, but they are also going to be challenged to think in the first year of studies. Not necessarily in my class, but actually in a separate engineering and context class. They're going to be challenged to think about how does technology shape culture? How does culture, in turn, shape technology? To recognize that technology alters the world around us and that engineers play an important role in creating technologies and managing it, and that we as engineers have a responsibility to be thoughtful, to really consider how our design solutions will impact communities, cultures, the world as a whole. And so while I teach design myself, I have colleagues in our engineering school that also, starting in that first year, in the very first semester, are teaching students to think about engineering in context. And what I then seek to do is in engineering design, I really want to challenge them to bring a technical thought process together with that broader consideration of the globe, the world around us. Now, we've heard a good bit in the discussions yesterday and today about flipped classroom. I do use a flipped classroom format in my instruction. I'm not going to make that a focus of my discussion today. What I'd rather do is highlight the efforts that I go through to motivate active learning. Rather than to have the students listen to me lecture, I want them engaged in thinking, to be the leaders in their own discovery process. And so really, what I work to instill in my classroom environment is a guided inquiry type of environment. And we use the design process, engineering design, as a framework for broader engineering education. One of the things that's very challenging for students in this environment, where I really put them as the drivers of their learning and knowledge development, is it's really a challenge for students to formulate questions. I don't give them the questions that they have to answer. I don't give them the solutions that they have to construct. But rather, the students need to be able to identify the challenge. They need to be able to construct the questions about that challenge. And then they need to be able to figure out how to develop the answers. How do they inquire and develop a knowledge? This just briefly is an example of the flipped classroom I'll provide each week to my students. A weekly lesson where I indicate that in a given week they will learn and have introduced to them new topics related to engineering design, and then there will be multimedia links and content similar to what we've heard in other discussions. And so the background foundational knowledge is provided to the students outside of class. They're expected to engage with that, and then when we come together, we're focused on the projects that they work on during the semester. So if we start in the first step of the process, defining a challenge space, what I do is I certainly organize the students into teams. These can range from maybe 3 to 5 students on a team. And then they have to identify their challenge. And this is an open-ended design effort. And so I really want to emphasize that I do not indicate to them what they will work on, but rather I say, you as an engineer need to be able to identify either a problem that you see in the world around you or an opportunity where you believe that engineering has an opportunity to make an impact in addressing the problem or capturing the opportunity. And this, you can imagine, is challenging for students at first. They say, well, what do you want me to work on? And I ask back to them, what do you want to work on? So we've heard a bit in the discussion yesterday and today about motivated and students that are not motivated. So one of the reasons that I've gone to this type of completely open format is in part to try to allow students to think about, to work on engineering concepts that are of interest to them. Not ones that I define, but ones that are particularly interest to them. And so I do not define the challenge space, and my goal is to have them working on authentic challenges around us in the world. In the early step of the first step of definition of their challenge space, I really focus students on performing research, but this is more what you might call library research. They need to read about, they need to discover, they need to fully understand the challenge space that they want to work on. And I actually work with them to divide that research into what I call internal and external searching. And I think sometimes for our students today, this is a little bit difficult. My idea of internal searching, the way I define internal searching, is asking a student to stop and think. What do they know about the challenge space? What questions can they ask about the challenge space? I really ask the students, don't speak to other people, don't get on the internet. Those sort of discussions with other people, those sort of investigations via the internet, those are part of external searching. But I think today, with the easy access of information on the internet, it's actually too easy for students to immediately turn to the computer to type in a search, and they don't think. I mean, the human mind is an amazing creation, and I need to challenge my students to use their mind as they first of all seek to define their challenge space and uncover knowledge and ultimately articulate questions about their area of work. So as an example, when my students then start to begin their process of engineering design, the type of areas that they will begin to work in could be things to do with security. Now, security could be personal security. So I have some students that are working on design of vests for police officers to wear. So bulletproof vests. I have students that are working on drone technology, flying drones, and thinking about security. How do you make sure that those drones do not stray into an airport or other secure spaces? We have students thinking about healthcare, the flow of traffic, things to do with clean water, energy conservation, sports equipment, things to do with pollution, including just waste, packaging, noise. Although we don't have earthquakes the way you do in Chile, a few years ago we actually had for us a fairly large earthquake, and all of a sudden, no surprise, my students were interested in earthquake protection or energy production. Now, one thing you can imagine as an instructor that is challenging for me about this is the variety of topics that students pick. So I'm their instructor, and I am not an expert in all of these different areas. But I actually see that as an educational opportunity, because as we go through the semester and we work on the design, the students can watch me struggle to help them to define what sort of tests they need to run on their solution concept. And so rather than always having the answer, always showing them a perfectly laid out lecture, they can actually see me working through the process of knowledge assembly, of asking questions, and ultimately helping them put a solution together. So at one point, initially, it's a very uncomfortable position for me as an instructor, but at the end, I think it's very valuable for the students. As they work to define their challenge space, they have to work early to define what are the requirements, what must this design solution accomplish. And so certainly you can imagine we always think this is an engineering design solution. It must function. It must perform. We always can think about financial considerations. If you're going to actually introduce your solutions into the market and really get society to adopt, it must be cost effective. And I also challenge students to define an additional set of requirements that I will call the X factor. So in our classroom environment, students must think about the performance, the engineering function, the cost, and then something else must factor into their definition of requirements. So what are some examples of this X factor? So it could be, for instance, something like the engineering in context. And I also have this idea of kind of a local lens. So the idea, say, of a local lens will be that in North America, as I think about designing a solution, I'm a product of my local environment. But perhaps here in Chile, you have different points of emphasis, things that are important to you as a society, as engineers, considerations. And so those sort of things might start to factor in here that for our community, Certain design considerations are more important than they might be elsewhere in the world. But other examples might be that here you think about the environment. And when I talk about energy and the environment here, perhaps as an engineer you're concerned about the energy required over the entire life cycle of a product, from the acquisition of the source materials, maybe in northern Chile, to the manufacturing process that might occur in Asia, to the energy used during the actual consumption of the product, or eventually the energy required at the end of the product life cycle to disassemble and dispose of it. So that's one example of the X factor. We might have social considerations. If we're going to have our products made in a certain location, what's the worker pay? Depending on where our product might be introduced and possibly used, there could be cultural considerations, things to do with the life cycle or the physical appearance, the aesthetics. And so this area, the X factor, I think is an opportunity where we can help students realize that now, as they think about some engineering design, they can frame the design process in a unique way that is creative, innovative, and distinct from something that anyone else in the world has created. Because it's unlikely that other designers will have put together considerations of functionality, cost, and this X factor just the way they have as a student. And so students can now put together a unique set of requirements that can ultimately lead to a unique design solution that they bring forward. So in step 2, they're generating now their concepts. They've understood the challenge space. They've said any solution is required to accomplish this functionality, this cost, this X factor. After they have those requirements laid out, they again engage in research. But now it's not research to understand the challenge, the problem, or the opportunity, but it's research as they brainstorm, as they think, as they look out in the literature to say, how are we going to address this problem? How are we going to seize this opportunity? And once again, I do not define the solutions for the students. They pick the challenge, they develop the solution, whatever it may be. So I guide them through the process of engineering design, but I do not define for them. Again, I ask that they engage in internal searching as they try to conceive of, imagine, how will we solve this problem? How will we seize this opportunity? What can their human mind think of? And so I ask them very deliberately, think internally first, and then go out, look at the literature, and understand what others have done in this area. This is really an opportunity, if we think about those higher order levels of human thought, creativity, innovation. This is an opportunity to really help students become creative and innovative. And if we think about the ideas of entrepreneurship, new business opportunities, the idea of intellectual property, these are concepts that even in the first year of engineering education, we can begin to show students the opportunities to be creative, to be entrepreneurial, to come up with unique solutions that could allow them as students, as individuals, to be successful engineers and business people in the future. As they get towards the end of the idea of coming up with different solution concepts, I do ask them to go through a very deliberate process of picking which solution, which concept is best. So we actually use a quantitative, a numerical decision matrix process where students will list out some of what they believe are their most promising ideas against what they feel are some of the most important requirements of their product. And then they're expected to put some numbers on this and ultimately identify numerically what do they believe is their best solution. So now the students have understood their challenge space. They've come up with many ideas, and they've picked one idea. And they say, we think this is the best, the most promising idea. So now they have to turn their attention to actually exploring that selected concept and really proving Is your concept viable? Does it work? Will it address the problem? Will it actually make an impact in the opportunity space that you've identified? And so in this area of exploration, the students are asked to now prototype, to create models of their solution. And the students are asked to either create a digital, something inside the computer, could be just design images, but it could be actually using computer modeling software to study the feasibility, the viability of their solution, or the students could be involved in creating physical models or prototypes. And so the students now have to think, what digital or physical model can I create that will allow me to run a test, collect data, and use that data against the requirements, and say the data that I have generated demonstrates or does not demonstrate that my solution will be successful. So the prototypes, once again, are not defined for the students. It's up to them to think about what is their solution supposed to do? What did they say that their solution was required to do? And so as an instructor, again, this is challenging because I am not necessarily an expert in all of the areas of activity that the students work in. But I understand the broad process that they should go through as they seek to evaluate their solution. So in this third stage of exploration, one of the parallels that I draw for our students, something that from their primary education, from kindergarten through 12th grade, they may be more familiar with, is the scientific method. And so I tell them, look, you probably, from your high school studies of chemistry, or earth sciences, or biological sciences, you have been taught to observe, question, come up with a hypothesis, experiment, analyze, and ultimately draw conclusions. And actually, that's not so different than what we're asking you to do here as part of the engineering design process. Initially, we asked you to observe a place where there's a problem or an opportunity in the world. And so as you defined the challenge, you were observing the world around you. Later, as you generated a set of solution ideas, in a sense, the question was, does engineering have a role to play in addressing this problem? Can engineering seize this opportunity? And then when they come up with their specific best solution, in a sense, they are hypothesizing. We believe that this selected solution concept can address the problem, can seize the opportunity. Okay, you have hypothesized that. Let's now experiment. Let's create prototypes. Let's test those prototypes, generate data, find out whether or not we actually are able to address the problem or seize the opportunity. And then just like in the scientific method, the students have to conclude, report out, and make recommendations, evaluate and assess whether or not their design actually is a successful design. So when we think about the prototyping efforts that go on, the students can create digital, they can use modern software tools, and I really do emphasize, I want students to go beyond just maybe a hand calculation. As those of us in engineering know, so much today, the computer modeling can be very sophisticated. And in the first year of engineering studies, the students won't understand the details of the computer models, but I do try to ask them immediately to use pretty sophisticated software tools that often students have free access to. Use those tools to do digital analysis, or perhaps to actually do physical creation, to make a testing rig. So here just is one example of some students that have begun to indicate how they might create a power-saving tool, create a little device and sensor that can identify when a device at home is consuming power, say in the middle of the night, and the students have decided, hey, we want to create a solution to turn off that power to save. So this is not an illustration, a digital illustration that they will use for analysis, but it does begin to prototype, to illustrate their concepts. But our students will go on. They will use fairly sophisticated software. Increasingly, we see students coming out of high school in the United States that already are familiar with digital design. So they use computer-aided design software. They already know how to do this, to draw images in 3 dimensions. And now what we do, even in the first year of undergraduate studies, is say, okay, you know how to draw in 3 dimensions inside the computer. Let's take the next step. Let's import those drawings that you've made, similar to drawings that my students here have made. Let's now import those design drawings into, say, a fluid flow software environment. Now, of course, in the first year, the students won't be very good at using these software tools. They won't always know how to confirm, did I generate a correct answer? But my feeling is in the first year, that's not quite so important. We rather want them to appreciate, to understand the type of tools that are used to explore and confirm whether a solution is a good one or not. And our students, in some instances, will take these designs, use rapid prototyping printers, and actually create the full physical model of their solution. We also have students, as I said, that will create physical prototypes. And for those physical prototypes, we have facilities that allow the students to begin to craft examples, models of their solution ideas. And not only craft them so that we can see them and understand what they want to craft, to manufacture, but to create things that they can use for testing purposes, to generate data and ultimately draw conclusions about the viability, the function of their design solution. And then at the end, the last step in our process is that the students have to report. They have to make recommendations about their design. And so in this part of the process, now we begin to have students involved in oral presentations, also perhaps in poster presentations, written form, learning to communicate, to verbally provide a project summary, say in front of their peers or teachers, or to make a poster presentation and be prepared to describe what they've created and what they've learned. In this latter part, I think this also provides in engineering an opportunity to introduce our students to the idea that sometimes, many times, as engineers, we're not successful. We fail. The majority of the time, solution concepts that are brought forward are not viable. And we try to teach our students that they shouldn't be scared about that. They shouldn't try to cover that up. So we can talk again now about engineering ethics. So I would like to believe that none of our engineers from the University of Virginia worked at Volkswagen in recent years, where they were asked to meet requirements on emission standards. And they couldn't do that. They failed at Volkswagen. But instead of admitting that their solution wasn't viable, they went to cover it up. So we can talk about that in this class, that, okay, maybe your solution is not viable. That's okay. You should still report. What did you find? And can you say, do you have a successful or an unsuccessful solution? From a learning process in this course, their grade does not depend upon success or failure. Their grade depends upon their ability to go through the steps of the engineering design process and be able to draw solutions. Now, my focus in the first part of this talk, the majority of this talk, has been on the first year of engineering education and working with students right as they join us in engineering design. But in our fourth and final year of instruction, we begin to do the same work with students. We have them involved in design activities and also ask them to think about engineering in context. And so in our final year, 12 credit hours, 12 out of 128 in that final year are focused on design and engineering in context. So from an engineering design perspective, our students might be engaged in developing a new solar water heater solution. But then as they think about engineering in context, they're considering how will renewable energies impact the function of energy markets. So the technical aspect of their design work, and then also thinking about the broader impact of their solutions. They may be working in a cutting-edge research area involved in the development of thermoelectric semiconductor systems. And then thinking about how to use, what are the barriers to introducing those sort of technologies, perhaps into solutions like automobiles. Or we have students that think about, say, the lifetime of nuclear reactor components, specific pieces of a nuclear reactor power plant, and then thinking about how communities react to the placement of a nuclear power plant in their community. So we focus on design, we focus on engineering in context, both early in our education of the students and also during their final year before they're prepared to go out into the workplace. And so when I think about design education and I work with the students, I really try to emphasize to them that, look, as we learn this engineering design method, what I want you to be able to do is ultimately make a positive contribution in the world. And so what I'm telling the students is I'm teaching you, I'm showing you how to make your way through from the start of an engineering design process, and through that design process you ultimately are able to reach the summit, say, of a local mountain. And I will teach you this in engineering design at the university. But the concepts that I teach you and that in school allow you to summit this small challenge. Ultimately, these tools and techniques should allow you to go out and use these same tools and techniques to address the greatest challenges in society today. And what we're seeking to do is equip our students with the skill set to make positive contributions to our world. As I finish my talk here, I want to look just for maybe 4 or 5 minutes at the end here towards the future as I think about engineering design. One of the things we've talked about just a little yesterday and today is the development of information technology in our world. So we've talked about the software tools that allow us to create flipped classroom environments. We know that computers are getting more powerful. We know the internet allows us to communicate in real time with colleagues around the world. And so I think, as an instructor at the University of Virginia, how can we make use of these tools to prepare our students for the challenges of tomorrow in a global society? And so I think a little bit about our undergraduate curriculum, where we start in the first year teaching our students about design, about engineering in context. We go and we build their technical and other skills in the middle years. And in the final year, perhaps they work on, yet again, engineering design. But what I'd like to see students, I'd like to help students begin to do is to go through this process of engineering design and engineering learning actually in a global setting. And so I'd like our students to start by connecting with one another in an online environment as they begin to learn about design, as they learn about engineering in context. Help the students maybe connect with one another a little bit over the internet, not leaving Temuco, not leaving Charlottesville where we're located, but speaking with one another, becoming more globally aware. In the middle years of their studies, perhaps they begin to go and study abroad. Students from Chile going to the United States, to Europe, to Asia, or students from the United States going to South America and elsewhere. Perhaps even students taking classes together, one another, students from Chile with students in the United States. And then at the end, in the 4th year, students being involved together in engineering design, where some of the team members are students in South America, in Chile. Some students are in the United States, learning how to work, not just on engineering design, but work across cultures and work on the greatest challenges of today and tomorrow. And so just very briefly, in the first year, I think students could start with separate activities where students learn design, students learn engineering in context, and then separately, students begin to talk to one another we actually are doing this fall, where we have students at the University of Virginia in our engineering school speaking to other individual students in their first year of study at other universities, beginning to develop a global awareness of students studying engineering elsewhere. Later, they can create personal connections. They can use the very simple and inexpensive tools like Skype, FaceTime, Google Hangout to connect with one another, think about engineering, learn about one another. In their middle years, we've also explored how can we have joint classes. So a colleague working with me has connected our students at the University of Virginia with students at the Technical University of Dortmund in a live, real-time, interactive learning environment, studying engineering, thinking about engineering in context. In this case, how is engineering performed in the United States? How is engineering performed in Germany? We can certainly support our students to be more involved in study abroad. And then what I would ultimately like to see at the end of the undergraduate studies is that after we have helped our students gain an appreciation of different cultures, after students have begun to use the tools of the internet age, and as students have learned about the design process, engineering design, we don't do this today. This is not a program of study that we actually run today, but it's my vision for the future that we would have our students from Chile, the United States, and elsewhere ultimately joining together on what I call global virtual design teams, solving the greatest challenges, because I actually think this is what we need when we think about the greatest challenges confronting us today, but I think it's also a great opportunity to leverage the intellect that we find all around the world. And so with that, let me stop, see if there are any questions. Thank you for your time and attention this afternoon.
Professor Gross, here. I have a question respecting to what you said when you talk about a lot about globalization, but I would like to know your opinion about integration with other careers. You talk a lot about engineers talking to engineers, but globalization and socialization also means that you have to share with people from other disciplines.
Yes.
Absolutely. What do you think about that? And if you have some experience about that?
Yes. So I think excellent question. Thank you. I think the connection between peoples, not just engineers in South America, North America, but engineers with other disciplines, is critical. And I'm serious when I say I think it's critical. Part of my background, I'm an engineer, but when I was studying in college, I also studied political science. So one of my undergraduate degrees is actually in political science. And so I really do appreciate the other disciplines. And I think, as an example, when you consider as an engineer, we're developing a technical solution. But now we're thinking about introducing that solution into different world communities. And those different communities are different cultures. And they have different mindsets. An engineer, a fellow engineer, is not necessarily going to be the person to help you really appreciate how do the people of Chile, how do the people of Germany think about this. You may need to bring in an anthropologist to help explain the differences in culture. You can imagine as you try to finance engineering solutions in different countries, there can be different ways that business is conducted. So absolutely, and in fact, when I teach in the senior year, we try to create multidisciplinary teams that go beyond engineers. Now, it's not always easy right now. We still have work to do, but I think that would be the ideal, is actually to think about design across our entire university and think about how we bring in different players from our students, say from politics, business, economics, anthropology. Because just like we think that engineering in context It's not just the engineering function, but it's all of these other considerations that ultimately allow you to get the solution into society to make a difference. You also need the people from all those other disciplines. Thank you. Good question.
Hi, James. I just have a question about the grand challenges that you mentioned. Can you be a bit more specific about what you see as the global challenges that we are facing now and into the future?
So I'll only give you a couple, Bernardo, maybe because here on the spot I can only think of a couple, but certainly something like global climate change. So I myself have a great appreciation of the outdoors. I love to be outdoors. I'm concerned about what engineering technology and world development is doing to the globe, the world around us. And I don't think that the United States alone is going to solve it. I think we, as a world people, are going to have to work together. Another example in a separate area that I think is quite the challenge, the internet is a wonderful, wonderful tool that has shortened the distance between us. We can communicate around the world instantly. But we also know that cybersecurity is a tremendous challenge, that now not only can I communicate, but criminals can gain access to my information. They can potentially disrupt my activities. So there's another example of an area where I think that working together could certainly make a difference. And then it was mentioned, I think, yesterday, you see in the United States, the National Academy of Engineering has put together a set of grand challenges in engineering. I believe there are 14 of those, and I think we could look at a number of those grand challenges as being areas of opportunity for cooperation. Thank you.
Just another one. I know that you're part of the Department of Engineering and Society, and it seems that research suggests that women tend to gravitate towards areas where they can make a positive impact on society. Have you seen that reflected in your programs? I mean, are you attracting more girls into that sort of focus area in engineering?
Yeah, so it's an excellent question. What I do know is that our engineering program at the University of Virginia has a fairly high representation of women at the undergraduate level. So our undergraduate engineering population is about 35% female, which in the United States is actually quite high. I think the average is more in the 20 to 25% of the engineering undergraduate population. Now, is our female representation higher because of the way that we present engineering? That I'm not sure about. But I do myself, this idea that as an engineer, the engineering skill set provides you the opportunity to make a positive impact upon society. That message and the way that I frame is absolutely intended to be an inclusive message. And I know through studies in the United States that talking about engineering as a way to make a positive impact is a messaging that has been found to appeal to women more so than some of the other messages used with engineering.
Muchas gracias.
Thank you.